Well, this is a short video on how to calculate the standard enthalpy of formation for any particular molecule in an indirect method. So we're going to use Hess's law, where if we don't know from elemental forms the formation of acetylene from carbon or hydrogen, if we don't know what the direct measurement of its enthalpy of formation is, we can use Hess's law. So this is sort of emphasizing Hess's law. And you say, well, when do you know I have to use Hess's law? Well, usually when you're given some question regarding standard enthalpy of formation for any molecule, and some data is given to you regarding other reactions that you're not interested in directly, but are using some terms that come into your equation. So when you're giving you some data, some standard enthalpy of formations for other reactions, and you're trying to find the standard enthalpy of formation for acetylene, probably going to have to use Hess's law. So we'll talk a little bit about this. Let's break down this problem, what they're asking for. They're asking for what is the standard enthalpy of formation for acetylene. So acetylene, let's put it on the right side. They want to know the standard enthalpy for formation of this molecule. This is called acetylene. Sorry. It's also just C2H2. We're going to refer to it as acetylene. We want to know the enthalpy of formation. Now, this term, enthalpy of formation, is tied to the heat given off or taken in when we go from the elements of carbon and hydrogen, the elemental forms, to the molecules. So we have the enthalpy of formation from the elements. This is from the elements. Enthalpy of formation. Formation from what? When you hear standard enthalpy of formation, they're assuming you're starting from the elemental form. So carbon in the graphite form, just going to put graphite, G-R-A-P-H, graphite, plus hydrogen gas, this is the elemental form of hydrogen. In those two states, when they're combined, the carbon in the graphite form, elemental form, hydrogen in the elemental form, how much heat is given off or taken in? And I don't want to just know delta H, I want to know standard. Standard, think of superscript circle there. There is a temperature and pressure that delta H is being measured at, or the heat transfer. This little circle here in superscript means, I'm just going to put an arrow to it, that means 25 degrees Celsius in 1 atmosphere. Standard, superscript there, circle, that means at 25 degrees Celsius and at 1 atmosphere for this reaction. So the reaction stays at 25 degrees and we stay at 1 atmosphere. How much heat would be given off or how much heat would be taken in by the system, by the reagents going to products? So this would be first state, just kind of talking a little bit in terms of thermodynamics. We have first state reagents. They want to know if I go from the state of, I need 2 carbon moles because that's 2 carbons over here in acetylene, so I balance that. So going from 2 moles of carbon in the graphite form plus 1 mole of hydrogen in the gaseous form, first state. If that reaction is completed and I go to second state, all acetylene, how much heat is given off or taken in? So that's kind of the idea. We want to go from one state to this second state. So I'm using dots here to represent the states. Now Hess's law is states such that it doesn't matter how we get from point A to point B, first state to second state, reagents to products. It doesn't matter whether we go direct and find directly the enthalpy of formation, standard enthalpy of formation, or if we go indirect. I'm going to put arrows to this later, but so let's say let's call this the intermediate point, something we don't actually want, but we may use on the way. And these are state functions. Delta H is a state function, so I'm really talking about sort of on a map, H values. I may know the difference between the H values from here to here and the difference in H values from here to here, and I could use that, according to Hess's law, to find the difference in H values from here to here. So that's where these equations come in. Let's look at these equations and the enthalpy of formation or enthalpy of reaction values that are given for these equations. If you look at this, it's really just oxidation or burning of carbon, hydrogen, and acetylene that they give us data for. It may not be the way we want to use it, but these are very commonly given. Oxidation of carbon generates so much heat, gives off 393.5 kilojoules per mole, or just say kilojoules. It gives off this much in kilojoules. This particular reaction, 1 mole plus 1 mole giving 1 mole. These are, again, values you may have for burning of carbon, burning of hydrogen. Say burning of hydrogen, we have 2 moles of hydrogen plus 1 mole of oxygen. When combusted, we get water forming, and it's in the liquid state here, not gas, because water at 1 atmosphere and 25 degrees Celsius is in the liquid form. So we have to go from elements to the molecule in the standard state. The molecule would be, in this case, of course, water, H2O. But it's in the liquid form because we're in standard states, 1 atmosphere, 25 degrees Celsius. And the heat given off, again, given off because it's negative. Negative means system's giving up that heat, is minus 571.6 kilojoules. Then the last one, a very large number, when we take acetylene and burn it. So these are all, again, burning. Burning of carbon, burning of hydrogen, burning of acetylene with oxygen. We have 5 moles of oxygen for every 2 moles of acetylene. We get, of course, CO2 and water. 4 moles of CO2 and 2 moles of water, and I didn't put it's in the liquid state. Ran out of room here. So these are reactions we can use, or equations we can use, to get us from what we want, carbon plus hydrogen, going to acetylene. We can use these equations, but we're just using Hess's law to derive that delta H of formation, because we can't measure it directly. We're going to have to use an indirect method. Hess's law. We're going to have to go to this intermediate state. So what I thought I'd do is just draw some pictures. So here's our 2 mounds of carbon, graphite, and I've got some H2 gas floating around. Now it'd be nice again to go right to acetylene, but I can't. I don't have that value. I don't know what that standard enthalpy of formation is. But I do have graphite going to CO2. I have that arrow, or that delta H of reaction. I have that right here, going to CO2. I also have H2 going to water, so I can go these mounds of carbon I can turn into CO2, and this gas of H2 I can turn into water, and I know the enthalpy of reaction for that. So I'm going to put next to these, this is for A and this is B. So you kind of think of it that way now as I'm at this point, I'm at that intermediate. So take a break, take off your pack, relax, pitch a tent, doesn't matter, we're now at this point, and now we can start looking for, is there some way to connect CO2 and water to acetylene, where I want to end up? And I think I have an equation for that. It's not in the order I want it. I have acetylene plus oxygen coming back to CO2 and water. So my arrow I have a, some story of how the enthalpy changed as I go from this state to this state. So you say, well, what do? I don't want to know the enthalpy of formation of CO2 and water from acetylene. I want to know the enthalpy of reaction to make acetylene from CO2 and water. So what can you do? Well, you can just take this equation, just like you can with this arrow, and flip it over and say, well, you know what? It's an equal and opposite distance and an equal and opposite delta H value. So if it was minus 2,599 to go this way, to go the opposite direction would be plus 2,599. If we change C, so we're going to change, I guess, C, we're flipping it. Because I need to have, this is my final point. I need that on the right side. Now I know I have some other things that I don't want, but we'll take care of that later. So I got that oxygen that I don't want, so I'm going to box that in. That has to be we need to take that out. I'm going to underline this because we want to keep that in our summation of these energies. We want to keep that on the right side. And of course, now the reagents became products, and products are going to be our reagents for CO2 plus water. If I have 4 CO2s plus 2 H2Os, I can make acetylene and oxygen. So at least now I have everything going in the right direction. I have from my intermediate state, if I could make CO2 and water and know the energy given, the heat given off for that, then I could know the amount of heat that I have to add in to make acetylene. It's 2,599 kilojoules. All right, so let's start canceling out things we don't want. So let's start using A and B. I'm going to put A and B as they are down here. Why? Because I know I have to start off with graphite. That's on the left side. And I know I have to start off with hydrogen. That's on the left side. I need carbon and I need hydrogen to be on the left side of this equation. So let's just leave them, and we'll change the coefficients as needed later on. So I'm going to write in carbon in the graphite form plus O2 gives me CO2 gas. Now I don't want this. This is my intermediate. I know that. And I'll wait for the energy here because of the enthalpy. I may have to change coefficients, but at least I have the equation down here where we're going to use it in the right form. Reagents on the left. And so that was A. Just rewrote A in there. And then B, we're going to bring B in. H2 on the left side. So I'm underlining that. Plus O2 gives 2H2O. And again, I'm going to wait to put in the exact energy because I may need to add coefficients. I may have to multiply or divide. And so how do you know whether to multiply or divide? Remember we have 5O2 that we need to cancel out. It's on the right side. I boxed it in. I want to get rid of that. We also need to get rid of these terms here. So we can leave everything in terms of carbon plus hydrogen makes acetylene. So we start having to think about how can we cancel things out. Well, let's go ahead and leave the bottom equation alone because we have right now cancellation of water. 2H2O on the right side, 2H2O on the left side. So without changing this bottom one, I can cancel this top one, this C that we changed. We flipped C. We changed it. I can already cancel 2H2O, 2H2O. But I still need to cancel the CO2 and the oxygen. So we could say, okay, what if I multiply by 4? So 4 plus 4 plus 4. So we're taking and multiplying everything by 4. That would cancel out the CO2. And let's check about our oxygen. 4 and 1. So that equals 5. So I can cancel out the CO2 with the CO2, and by multiplying A by 4 times this equation, I can have cancellation of oxygen. So now what I'm left with, the summation is, and I'll put the energies in. I just want to make sure this works here. I have acetylene on the right side. I've canceled out the oxygen because I multiplied A times 4. And I left B the way it was, so 4 O2s plus 1 O2 on the left side is equal to 5 O2s on the right. That canceled out. So we can say, okay, that's canceled out, the oxygens, and the carbon dioxide canceled out, and the water canceled out. So all I'm left with is 4C, graphite form, plus 2H2 gas form, gives us C2H5. Now we have to start talking about these energy or these enthalpy values. I took 4 times A in the form that it's in. So just taking your calculator, turn on here. There we go. We can take 393.5 times 4. It's still in the negative, so it's minus 1,574. And we still have B is minus 571.6. We didn't do anything to that one, and we flipped already C. So we should be able just to add these up, and that'll give us our, I apologize, I think I made it, that 2 here. Apologize, we still had the 2 there. So that would be, 2, and we can deal with that. If this is 4 plus 2 plus 2, we can take that value that we come up with and divide it by 2. Since this is 4 plus 2 giving 2 moles, we can take whatever value we get and divide it by 2. So let's take 2,599 and subtract these two numbers. 2,599 minus 1,574 equals, and then minus 571.6. So for this reaction as is, we would have to add 453.4 kilojoules of energy to have this reaction go. But we don't need 2 moles of acetylene. We just wanted 2 of the graphite plus 1 mole of hydrogen to make 1 mole of acetylene. So what do we do to this value? Just divide it by 2. So we can take this value and divide it by 2. And we get that the delta H of formation for this reaction is 226.7 kilojoules per mole. And we used an indirect route, Hess's law, to get there. Well, that's a mouthful. If you have data given on other reactions around the direct reaction you need to determine the delta H of formation for, the standard delta H of formation, you may have to reorient these or flip these in order to have cancellations so that you're left with the elemental forms you need and the molecule that you want to find the enthalpy of formation for, the standard enthalpy of formation. Well, that's it. Bye-bye.